Hello, thanks for tuning in. This is Baboons on the Move's project update for the Spring 2020 Embedded Systems Design class. My name is Christy Walters and my partner is Josh Kang. We've been helping out with an Engineers for Exploration project that helps primatologists track baboon troops using aerial footage. You can find out more about Engineers for Exploration, where students use engineering skills to drive academic research, by visiting this website. Although this video will try to focus on our individual contributions, we worked in collaboration with the existing members of this team. Several of the models I'm going to show you were created all or in part by Chris Crutchfield, An Guo, Alvin Wang, Yujin Huang, and other collaborators from previous quarters. Also, the footage of the troops that we worked with was provided by Neil Thomas. With that, let's get started with the state of the project at the beginning of the quarter. Back in March, the Baboons on the Move team had created a binary motion model that's able to pick up some of the baboons moving in the camera footage. You can see here that it's picking up some of the baboons, but they actually have no way of measuring the success of this mask. The team was just comparing results by looking visually at the video. We also had a drive full of data that researchers had hand-labeled using the Elon annotation tool. This data would act as our sources of truth, but it's yet to be utilized. Alright, so what was our plan? Our goal would be to improve the baboon detection algorithm by implementing a particle filter. This would be done simultaneously as other members of our team worked on a Kalman filter. It seemed more worthwhile to try both methods and compare the results. In order to do this, we would need to extract centroids from the motion mask, a measurement of the success of the model, to obtain centroids and velocity data from the sources of truth data, a motion model that can make predictions of the baboon's location, and a particle filter to tie it all together. To start off, the other members of our team created both blob detection and contour detection methods to extract centroids from the motion mask. I was working on a script that could extract centroids and calculate the velocities of all the baboons in the ground truth data, and if I can put it into a Python-friendly CSV file. Using both CSV files, I used a KD tree to find the nearest ground truth centroid to each baboon that was detected using the blob and contour methods. I measured the Euclidean distance to determine 1. How many pixels away are each of these points from the ground truth data? And 2. How many instances of the baboon out of all the baboon instances in ground truth is this method going to pick up? The results ended up roughly the same. Both picked up the majority of baboons within 25 pixels, but only picked up about 10% of the 25,000 baboon instances. Because they're roughly equal, we went with a blob detector. Going even further, I grabbed the velocities from the corresponding ground truth baboons to do an additional comparison. The motion mask only picks up movement, so I wanted to visualize what speed the baboons move at and what speeds does the mask pick them up at. On top is a chart of the velocities in pixels per second of all the baboon points in the ground truth data, and on the bottom is all the points picked up by the blob detector. The blob detector does pick up a lot of unmoving baboons, but it's substantially less than all the baboons present. Now if I divide these results by each other, I get this chart, which indicates on the y dimension what percent of all the baboons moving at a velocity the blob detector is picking up, and on the x dimension is the velocity in question. We can see that the blob detector works best when our baboons move 60 pixels per second or faster, but our baboons move much slower than that most of the time. This is just good data for us to understand how the model is running. There's some methods that rely almost completely on blob detection for this kind of task, but in our case, I really don't think that would be possible. We created a motion model for the particle filter that uses states to predict movement. These states would be based on the velocity of the baboon, like are they walking, are they running, what are the chances that if they're running, they transition to walking. We also take into account the states of the 5 nearest baboons as well. The model trained well, starting off with a loss of 1.4 and converging to somewhere around 0.15. Finally, we get to the particle filter. We were unable to finish all parts of this by the end of the quarter, but we are about 95% of the way there. When the particle filter is finished, sometime in the summer, it's going to create an improved estimate during occlusion and allow us to differentiate baboons in the footage. Thank you for your time, and I hope you have a great summer.